Hey everybody, it's Wednesday, November 25th, and as you can see here in the aim today, the focus of this video is just going to be all about explaining to you what you're going to do for the lab. So as you probably got the idea from the pre-lab assignment yesterday, today we're going to be doing an experiment where we are trying to measure the coefficient of friction for two objects in contact. And so yesterday, in order to prepare you for this lab, I asked you a series of questions. And what I want to do in this video is just go over the answers to those questions and then get into a little bit about how exactly you're going to use the website to do the experiment. So the first question in the pre-lab assignment yesterday said, in one of my videos, I showed you what can be referred to as the characteristic drag test graph. In the video on AP Classroom, which I assigned to you yesterday, this graph is shown as well. Make a quick sketch of the characteristic drag test graph, which notice is a force versus time graph, and label on the graph where the static friction force maximum value is and where the kinetic friction force value is. And so as I mentioned here, this is a force versus time graph, and so we're going to have our force in newtons on the x-axis and time in seconds, force in newtons on the y-axis and the time in seconds on the x-axis. And the characteristic drag test graph is going to look something like this. Of course, the lines are going to be a little straighter than I've drawn them, but for the most part, it's basically going to look like this. And so the second part of the question, which said, identify the spots on the graph which show you the maximum static friction force and the kinetic friction force, the peak of the graph here is the static friction force maximum. And this flat part is the kinetic friction force. And so when you are doing a drag test, this is how you use the graph produced by that drag test to determine what the static friction force and the kinetic friction force are. Now, if you notice, what we said we were going to be doing was doing an experiment where we measure the coefficient of static friction and the coefficient of kinetic friction. And so the question here is, well, what do we actually need to measure to determine the static coefficient of friction? And what do we need to measure to determine the kinetic coefficient of friction? And as I mentioned multiple times now by this point in the year, the way that you figure out what to measure in an experiment is entirely dictated by the equations. And so if you use the equations for the force of kinetic friction and the force of static friction, then you will see that when you solve those equations for the coefficient of friction, you get something that looks like this. And now we have an interesting little question to answer here, because we have to measure the static friction force maximum, we have to measure the normal force, and we have to measure the kinetic friction force, and we have to measure the normal force. I think the question ultimately is, well, how do we do that? Something that you should notice by now, for sure, is that when we have these objects on a flat horizontal surface, the normal force is equal to the weight. And since the weight is just the mass times the gravitational acceleration, all we're going to need to measure the mass is a scale or triple beam balance. And so if we have a scale or a triple beam balance, then we can definitely measure the mass, and we can use that to calculate the normal force. But of course, we've got an interesting dilemma here. And that's because if we want to measure the static friction force maximum and the kinetic friction force, then we're going to want to use a force sensor. But of course, if we are dealing with an object sitting on a surface tied to a string, and we are pulling the object with a force sensor, that force sensor is measuring the applied force. Now, this is an important thing to bring up, I think, because this would be a real practical concern if we were actually doing this in class. But because you're going to be using a computer to do this, I think it might sort of mask some of the difficulty that might be involved in this kind of problem. And so it's important that we just take a moment to address this head on here. The question is, we only have very specific situations where measuring the applied force is going to give us the force of friction. And so the big question here is, what are those circumstances? And it doesn't matter if we're talking about static friction or kinetic friction, the circumstances in which the applied force and the friction force are equal are circumstances in which the acceleration is zero. And so that's why if we go back real fast and look at the kinetic friction part of this drag test graph here, this is why this force is constant. It's constant here because we are going to be pulling this block at a constant speed. Now, you're not actually going to have to pull anything using this website, but when we are actually doing these things in class, it's a really important concern that we have to have, that when you're pulling the block, like somebody in your lab group physically pulls the block, you need to make sure that it's pulled at a constant speed so that the measurement on the force sensor is actually the force of friction and not just the applied force, which would be bigger than the force of friction if you made the thing speed up. Moving on to question 3. Question 3 says, if we're going to produce two graphs, one where the slope is equal to the static coefficient and one where the slope is equal to the kinetic coefficient of friction, then what do we need to put on the y-axis of each graph and what do we need to put on the x-axis of each graph? Again, as was mentioned in the answer to the last question, all of this stuff comes down to the equations. And so if we put the equations up here again, we actually don't even need to think too hard about it this time. And we don't need to think too hard about it this time is because this already takes the form of the slope is equal to delta y over delta x. So if we plot the static friction force maximum on the y-axis and the normal force on the x-axis, then the slope will be equal to the coefficient of static friction. And likewise, if we plot the kinetic force of friction on the y-axis and the normal force on the x-axis, the slope of that graph will be equal to the kinetic coefficient of friction. And that's the deal. Whenever you are trying to describe how you're going to analyze data from an experiment, it's the smartest way to do that is to talk about what the graph would look like. And that's a really smart idea because it sets you up for describing the whole procedure, because the procedure here is going to be pretty straightforward. Notice that's really what the last question gets to. Last question gets to here is, how do the requirements for the graph inform us about how we're going to perform the experiment? What do we need to measure? How do we determine the things we're going to plot on the graph? Well, it all comes down to the graphs. And so clearly, to measure the normal force, we're going to need the mass of the object. And so you're going to put that in a data table for sure, the mass of the object. You're definitely going to want to measure the static friction force maximum and maybe do like a trial 1 and a trial 2 just to see if you get the same or different values and then average them together. And then do the same thing for the kinetic force of friction and then average those together. And of course, put the units in all these when you're making a data table. And so the idea here is that in order to do this experiment properly, we're going to want to measure the mass of the object, the force of static friction, the force of kinetic friction. And doing this over multiple trials with multiple different masses here is going to allow us to fill in the rest of the table. So how's this going to look? Well, if you click on the link in the assignment today, then you will see a website called thephysicsAviary.com with an interesting little friction lab. And so if you click the experiment, you will see exactly what we have to deal with. And so first, notice they give you different types of surfaces. Just to make sure we're all on the same page, let's just all put this on wood on lab table. And you do it just by clicking the words there. If you click the words, you get to wood on lab table, you stop it there. I also want to point out that you can change the mass here by clicking these arrows. And it's important to notice there are 18 different mass options that you can use. I am not asking you to do this for all 18 masses. What I will say is that the more masses you do, the better data you will get. And so I don't think 100 is a good one to start off on. I would say at least go to 200. So I guess start at 279. And then notice when you hit start, the person's now pulling. You see the force reading on the force sensor change. The force goes up, and then it goes back down when you're getting your kinetic friction force acting here. Now, the obvious question is, wait a second, is that how I'm supposed to do this experiment? Just look at that force sensor and see when it peaks and then what it's averaging at there? No, but I do think it's a good idea to look at. The way you're going to get that is with the graph that's underneath. Now, they didn't show the vertical part of this graph here. They just showed it as being discontinuous, but notice that's what we're dealing with. And so you're going to use these graphs that this thing produces. You got your static force of friction there. And of course, maybe you can draw a straight line in there or something. You want to take about the midpoint of all those clusters of points. And then notice here, they're fairly spread out as well. And so you want to go ahead and take the midpoint down here, and you'll have to determine whatever that is. And you go and collect your data. This is for 279 grams, of course, as I showed here. You're going to want to convert that to kilograms. And then you plot your values. You put your values for these things in the graph. Of course, you're probably also going to want to make a section of this chart for normal force. I would actually put that right in here. Although you could do it on a separate table as well. A separate table might actually be a smarter idea after you get like all of the raw data in this data table. If you go and make one more data table that just has the forces, and now you separate these because you are making separate graphs. And so we have the force of static friction maximum values and then the normal force values. And notice this is kind of like how they had it in that AP classroom video. And so you have all your different little entries here, and then you can just use those to make your graph. And that's it. Should be pretty straightforward. And so what you are being asked to do today is all entirely in that assignment posting on Google Classroom. But the basic idea is you are going to make a raw data table like this. You are going to use that website to fill in the raw data. And then you are basically going to make two charts like this. One of these charts is going to say the static friction force maximum versus the normal force, and then you're going to make your graph, get it to calculate the line of best fit, and show you the slope. And then same thing for kinetic friction force. And that's it. And because I am assigning this lab to you over the long weekend, I mean, really, I'm assigning this to you today. This is the only thing you have to do for class today. But because the next time we're going to meet is over the long weekend or after the long weekend, we'll make the official due date that Monday morning, because in the video on Monday morning, I'm going to address basically the results that you should have gotten from this experiment. And that's it. Go ahead, do that lab, and if you have any issues, questions, or concerns, then just let me know in comments or email. All right, everybody, have a nice weekend and enjoy Thanksgiving, and I'll see you back on Monday. Take care.